Hello and welcome everyone. Thank you for joining us today for our webinar titled Responsible Automation Towards Interpretable and Fair Auto ML. My name is Shabar Pula and I'm on the marketing team here at H2O.ai. I'd love to start off by introducing our speaker. Aaron Liddell is the Chief Machine Learning Scientist here at H2O.ai. Before I hand it over to Aaron, I'd like to go over the following housekeeping items. Please feel free to send us your questions throughout the session via the questions tab. We'll be happy to answer them towards the end of the webinar. This webinar is being recorded. A copy of the webinar recording and the slide deck will be available after the presentation is over. Without further ado, I'd like to hand it over to Aaron.
All right, thanks, Shabar. So yeah, today we're going to talk about I guess sort of a new topic that we haven't spoken about too much in our webinars and meetups in the past. We certainly have had a lot of webinars about interpretability, but the focus of this talk is even a little bit more broad than that. We're going to talk about algorithmic fairness and a bunch of social issues related to using machine learning and how it has an impact on the world. So yeah, thanks for joining us today. It's a really becoming a very big topic. There's becoming a lot more discussion and conversations and attention to these issues, and I'm happy to be a part of that. So yeah, most of the time when I give a talk, I pretty much just talk about AutoML or H2O or things like that. So this is just, we're not going to talk too much specifically about H2O today, but just about this topic in general. So I'm going to skip to the next slide, which will just give you an overview of what we're going to talk about today. So I am going to just spend a little bit of time defining what is automatic machine learning or AutoML, and then what do we mean by interpretable and fair AutoML, and then I'm going to have a little bit of a discussion about like when is it maybe actually inappropriate to use machine learning altogether to solve certain problems, and then kind of where do we go from here. And I have a link at the bottom, which is, I gave a talk similar to this at the UseR conference. I was one of their keynote speakers this year. That was about a month ago. And so I put together a little demo and I have it, I'll go over the demo as well. And if you go to that GitHub repo, you can find the code for the demo that I'll go through. And I'll give you that link again later, but it's there now if you need it. Okay, so what is automatic machine learning? So this is generally something I would present in a normal AutoML talk. So I would talk about the goals and features of AutoML. So, and then we'll move on to some of the negative side effects of AutoML. But for now, we're going to stay positive. So this is just sort of my opinion. AutoML is not a well-defined term. It's kind of used broadly to describe a lot of different things. So I'll just try to talk about, rather than try to focus in on what is the actual definition of AutoML, I'll try to say some of the goals or features of AutoML, at least in my opinion. So one of the main things that we do in AutoML is to try to train the best model that we can in the least amount of time. And by that I mean time in terms of how long it takes to train, like computation time, but also in terms of how long does it take the data scientist or user to come up with the code to actually do that experiment. So there's kind of two pieces where we can try to reduce effort. So just computation itself, and also just how difficult is it to set up all the code and run the experiments and train the models. So AutoML tools sort of hope to minimize both of those aspects. So that kind of brings us to the next point. I mean, this is sort of a goal, but also a feature. Having AutoML tools reduces the human effort and expertise required to do machine learning or data science. So, I mean, basically, all you need to know to do AutoML is some basic things about data science. Like you have to know what a training set is. You have to know how to measure the performance of a model, or at least understand like what metrics are appropriate for certain cases. But the things that you don't need to know is like all the details of all the different algorithms that you could use, like GBMs, gradient boosting machines, generalized linear models, deep neural networks, random forest. There's all these different models that you, as a data scientist, have to know how to use and how to tune. AutoML makes it possible to not have to know all the details about every single algorithm. You just have to know the basics, and that makes it very accessible to people that are either new to data science, or also just it speeds up quite a bit the process. Even if you're a very experienced data scientist, you can do more with your time. And then one of the other goals is really just across the board, we're trying to get better models than you would be able to just by handing it over to, a data scientist on your team. Maybe if you have a really, really sophisticated data scientist who has like 10 years of experience, et cetera, like they're probably still going to be able to beat pretty much any AutoML system out there today if they put enough time and effort into it. But that's not really necessarily the goal. The goal is just sort of handing it over to an average data scientist. Hopefully an AutoML tool would get a better result than you would be just not using an AutoML tool. Another thing that is nice, which maybe is something that people don't talk about that much as a feature of AutoML, but one thing that I've seen it be used for and used well is just to have a function or a tool that you can use if you're some kind of scientific researcher or, either in industry or in academia, you're trying to do, let's say you're a neuroscientist and you're trying to use machine learning for the first time on some problem. And so what I see generally is, people that are a little bit familiar with machine learning, they might say, okay, I'm going to train a random forest on my data and show these results and publish a paper. When I read that paper as a machine learning person, I say, oh, well, that's interesting to see how well they did on a random forest, but I'm actually curious to know in general, how well could they have done on that problem? Like how well could it be solved by machine learning? And, they didn't try a whole bunch of things. They just did, the simplest thing that they were able to do. So if you really, if you're not an expert at machine learning, but you're using it as a tool for some other purpose, an AutoML tool is a great thing to do, because then you kind of answer the question of what is, if you put a really good amount of effort into this problem with machine learning, what would you be able to accomplish? And so not only are you able to establish strong baselines for new problems in scientific discipline, but you can also increase reproducibility because, anyone can just very easily use your AutoML tool and replicate your results. It's not hard to reproduce. So those are some of the benefits of AutoML. And if, maybe you've, have more that you could add to this list, but this is just a short list. So next I want to say, this is usually where I stop and then I move on to some other things about AutoML and how it's so great. But for this talk, we're actually going to go into, some of the negative side effects of AutoML. So it's a great thing, but just like a lot of tools, they can be, they can have good aspects, there can be negative aspects, there can be harmful aspects. This, again, AutoML is really just a tool, so it's how do you use it is really what matters. So one of the great things, like I mentioned about AutoML, is that new or novice data scientists can easily train models. But if you flip that over, then what that also means is you're having a bunch of people that maybe don't know that much about machine learning easily creating a bunch of models and maybe even pushing them into production. And so if there are any mistakes that are made, we're sort of increasing the chance that, bad models end up in production if there's people that are, let's say, less sophisticated or less experienced or don't know what to look for in charge. So if, this is the same thing, same bullet point as I had on the other side. This is just looking at it from a different angle. So there's definitely a possibility that we could increase the amount of sort of bad models that are out there in the world doing things that we don't know about and they're not being tracked properly. So, and most AutoML systems have pretty minimal guardrails in the sense that their only goal is to get you a good model and they stop there. There's not a lot of here's your model, but here's some of the things that you might want to look out for if you use this model. Maybe it's not so robust to outliers, or maybe, this and that. So what I would like to see is more guardrails on these things. So we're making it so easy, but then we're sort of, at least to this point, maybe not doing enough to assure that we're making it easy for you to do the right thing and evaluate your models properly and not push a model into production that probably shouldn't be there. So another thing that I've noticed is, like, when you have an AutoML tool, you can really just essentially automate creating a whole lot of models. Like, consider the scenario where you're a company and you create a model for each user. Let's say you run a website, like an e-commerce website or something like that, and you actually train a single model for each customer. So with an AutoML tool, you could very easily do that. Let's say you have 100,000 customers. So you basically write a script. You can train 100,000 pretty good models, and you could just push them all into production without looking at them. So we're kind of speeding up or accelerating the process of creating the models, but at this point, there's not a lot of tools for auditing those models that are also automatic. So you have this wide, big, vast pool of models that have been created, but then you actually still kind of need humans to look at each one of them and to make sure it's okay and there's not anything funky happening. So there's a bit of a gap in terms of how do we automatically audit these models or look at them as well. So that's all stuff that could be improved in terms of AutoML software. All right, so let's see. What else do I want to say about this? So yeah, just in case you're unfamiliar with what kind of bad things might happen. So just one example I'll give in case this is new to you. So when I say like a bad model, what that could mean is not that there's anything wrong with it going into production, but what if over time there's sort of a shift in the data and there's nothing like maybe the data scientist doesn't know to check for that. So when you train a model on a certain type of data, the expectation is that the future data or the test data or the real life data will be very similar to the training set. And often that's not the case. Often there's data that kind of changes over time. So if you're, let's say, a newer data scientist and you're not aware of these things, like that you have to monitor models in production, things like that, then maybe the model starts to give bad predictions and it's starting to have all these negative effects and all sorts of weird things can happen. So these are just things that, if as you're a data scientist and you get experience, especially working in industry, you'll know to look for these things. But maybe people that are new to AutoML and just, trying to train models for the first time might not be aware of them. So, these are just some things to make note of. Okay, so I am going to talk just briefly about what is H2O Auto ML. So this is the project that I'm leading at H2O. So the company itself, we have a number of different software products. So H2O is one of them. That's our open source machine learning platform, and there's an algorithm called AutoML inside of there. We have other tools. There's a tool called Driverless AI, which is a proprietary AutoML solution. So you can think about these things for any AutoML tool, but just because this is the tool that I create, I'm going to tell you a little bit about it. It's open source. You can try it out. So what do we have here? I'm also just using this as if you've never seen an AutoML tool before, and this is just one example of what it could look like. So with H2O Auto ML, what we do is we do some basic data pre-processing. This is stuff that we do in all the H2O algorithms. It has to do with things like filling in missing variables, automatic encoding of categorical variables, things like that. So just anything related to the data, we automate. Then we select all of our algorithms that are pretty strong, like gradient boosting machines, deep neural networks, GLMs. We also have random forests. We have XGBoost. So of each of these algorithms, we do sort of a random search on them. So we'll train a bunch of GBMs. a bunch of, so when I say GBMs, H2O has its own GBM, then we also have the XGBoost GBM. So just to be clear, it might train a bunch of XGBoost models, a bunch of deep neural networks. So the reason we train a whole bunch of models is because it's pretty hard in advance to know what algorithm is going to work best for your data, and then what hyperparameter values are also, going to work best for your data set. So most AutoML tools focus on just a large exploration of lots of different models, and then that's kind of how they find a good model. And the difference between all the AutoML tools out there is just whatever technique they're taking to do that exploration. So some tools use techniques like Bayesian optimization, genetic algorithms. There's all different approaches. So this is our approach. So but basically they all have the same goal, to try to find a good model. So each of the individual models we try to tune to make sure they don't overfit. We do that using cross-validation. And then once you have your set of models, you will train 2 stacked ensembles. So stacked ensembles are just a sort of a super model that contains a bunch of what we call base learners or base models. And the goal there is to get a better performing model by using all these individual models as the components. And I'm not going to go into too much detail about that, but it's just a pretty straightforward way to get a better model by combining the models that you have into what we call an ensemble. And then at the end, what you get back, you get this thing that we call a leaderboard. And basically, I'll show you what that is in a minute, but it's sort of just a ranked list of all your models, and then, sorted by some metric, and then the one at the top is the best, and then you can just choose that one and move on to the next thing, or you can sort of look through your list and see, you can sort by different things. If you have different desires, like let's say you care a lot about prediction speed, you could actually try to find the best model that was also very fast to make predictions in production. So you can sort by different attributes of the models, but we'll by default just sort by performance. And then because we're working in H2O, all these models can easily be exported to production. So that's just kind of like a high level overview of what one example of an AutoML system does. And then I'll also show you just actually some code, like what that would look like. So this is what it would look like in R, and the next slide I'll show Python, but and then the slide after that I'll show our GUI. So like if you're not a person that writes code, you can also train it in the browser. But basically it's very simple. You upload your training data. You import the library, you start the H2O cluster, you import some data, which is your training data, and then you run this function that's called H2O.AutoML. And all you need to do is say, here's what my training data is, here's the name of the column that I'm trying to predict, so the response column or the outcome column, which is in your training set, and then how long do you want it to run for, basically. So this one's saying run for 10 minutes and then be done. And then you get this object back, and one of the main items in the AutoML object is the thing that I described earlier, the leaderboard. And I will get into more detail about that, but here's the same thing of what it looks like in Python. There's just one extra line of code because that's kind of the more Pythonic way of writing this code. So you set it up, you say run for 10 minutes, and then you tell it what data you want it to run on, and then it runs, and then you get back the leaderboard. And then quickly, I'll just show you what that might look like in the GUI. So when you use H2O, you have this, anytime you use, even from R or Python, what it does is it starts up a local web server on your machine, which is serving this website. And so at any point, you can go to type in a certain address in your browser, the default being localhost port 54321, and then this thing will pop up, and it's just sort of a GUI, like a web GUI for H2O. So you can run AutoML that way as well, so no code necessary. And then I would say not all the AutoML tools out there have this concept of a leaderboard, but I'm seeing it more often. Sometimes they just return the final model that they found, and they say, here's your model, and they kind of throw away all the other models that they trained along the way. we take a different approach where you can use any of the models that you spent time training. We will sort them by certain metrics, but you know, they're all there sitting in your memory, so you can take whatever one you want. And in this case, we try to give you, you know, simplify this thing as much as possible. So we just have model ID to identify the model, and then we have a bunch of metrics. This is what we call the default leaderboard, where you don't have extra things like training time, prediction speed, etc., just metrics. So you can kind of see here, like this is an example. We have stacked ensemble is doing the best, and then and there's another stacked ensemble slightly behind that. Then we've got XGBoost is in number 3. And if you want to look at what those models actually are, you just grab the model by ID, and then you can look at all the hyperparameter values. You can plot things. You can do whatever you want. So yeah, you can kind of, we at least give you the name of the type of model it is, so you have some idea about what's happening on your leaderboard. But yeah, so that is kind of my just brief overview of what is AutoML in general and what's an example of what that looks like. So now I'm going to move on to something else. So this is more the topic of the day. So what does interpretable and fair AutoML look like? So there's lots of, first I'm going to talk about interpretability. There's a lot of different interpretability methods out there. I'm not going to have time to list them all, but I'm going to give you one example of what is something that I mean by interpretability and how can that help you in your process. So one of the things, one of the tools that I love for interpretability is just something very simple. It's called a partial dependence plot, or PDP. And what that does is, I mean, if you're not familiar with statistical terms, this might seem a bit dense, this definition, but I'm just going to read it out to those who are. So it shows a marginal effect of one or two features have on the predicted outcome of a machine learning model. So what does that mean? So that means that on the x-axis, you have some feature in your data, some variable in your data. So let's say we were trying to, I think this data set is from the demo that I'm going to do later, which is you're trying to predict whether or not to give somebody a high interest or low interest mortgage or loan. So in doing that, you would want, I mean, the reason why you give somebody a high interest mortgage is you're kind of afraid they're not going to pay it back. So you would look for things that would be indicative of that outcome. So one thing that they put into these models is just your income. And the idea, I guess, would be like, as your income increases, your ability to pay your loan probably also increases. So in this case, it's actually, we're predicting the reverse of that. So we're actually predicting whether or not you're going to get the high interest loan, which is sort of the bad outcome. So as your income increases, you would expect your likelihood of getting that bad loan to go down. And so that's something that you can actually verify with a partial dependence plot. And we actually do see this trend somewhat here. So at the very beginning, where you have really small numbers for the income, it's a bit, you know, doing something weird there, but then it sort of levels out over time and sort of goes down over time. So one thing that you could do is, let's say you really wanted to force that dependence of, for whatever reason in your data, your machine learning model learned that there's some kind of inverse relationship at the very beginning when you have very low income, and then it kind of does the thing that you would expect as your income increases. But if you actually wanted to force that in your model, there's ways that you can do that. You can say, I want to force a monotonic relationship between the income variable and the outcome. And so that would be something that you might do. Like, you train a model, you see that you kind of have the relationship with what you want. The model kind of learned that, but you want to force it. You can actually retrain the model and force that relationship. So this is kind of like why a human is often in the loop for these interpretability methods. So yeah, so that's just one example. Let's see. Let's go to And that's a function that we have in H2O. I just plotted that function, or that plot from H2O itself. There's a number of other things related to interpretability, but I won't go into so much detail there. So I want to just move on to a bigger topic, which is fairness in machine learning, or in other words, algorithmic fairness. So you might have heard that term before. It's also one of those terms, like AutoML, that's not super well defined, and it can mean a lot of different things to a lot of different people. So when you say, what is fairness in machine learning, it's kind of a hard question to answer. But I think maybe the best description is that it really describes a broad set of problems. So I would like to discourage people from thinking about it as in sort of a reductive sense, where you're like, is this model fair or not? Yes or no, tell me the answer. It's a much more nuanced thing. And so my first sort of recommendation would be to not try to think about it in those simplistic terms, but think about it as just an overall thing. It could involve evaluating the models. It could involve evaluating the data set. It could involve evaluating like the social impact or circumstances around the data or the problem, or what could be the impact of using machine learning for that particular use case. So it can really relate to any of these things that are technical and sort of more social science issues as well. So one of the reasons why this is kind of a hard problem to sort of assert that your model is fair, or try to, understand if your model is fair, is because there's also lots of different types of fairness, and sometimes they're in contradiction with each other. So there's a couple different notions of fairness. One is individual fairness, and what that means is, like, if you have two data points, and in this case, let's just assume that in the training set, all of our data points generally represent people. When we're not dealing with people, we don't have to think about these things of fairness as much, but if your data set is actually representing people and certain outcomes, let's go back to the mortgage lending example. So each row of your training set is somebody applying for a loan. So those are actual people. So think about rows as people in your data set. So with individual fairness, you want to make sure that if you have one person who's applying for a loan and you have another person that's very similar to that person, that you kind of get the same outcome. Like, if you don't, there's probably something wrong with your model. So that's like one thing to check for, is if you have two people very similar to each other, you should be kind of getting the same outcome. And if you didn't, that's the first step that you need to fix. But then probably the more common notion of fairness has to do with comparing different groups to each other. So let's say, usually we're talking about demographic groups. So we could talk about gender, we could talk about race, we could talk about ethnicity, we could talk about age. There's sort of a list of, at least in the U.S., so there might be people on this call that are outside of the U.S., and the rules are different in every country. So also when we talk about fairness, there's sort of this sort of lurking thing in the background that's like in relationship to what laws, like, because the laws are different in every country, and then maybe different cultures have different sense of what's fair, and it gets very messy very quickly. So, but just to try to simplify it, when we're talking about group fairness, it's like, let's compare how the model affects white men to black women, for example. That's a pretty common comparison, and usually the models do not work the same on those two groups of people. And generally it has, there's a lot of reasons why that is. A lot of it has to do with data and representation in the data. A lot of it has to do with just, implicit social issues that created the differences in those data, that maybe those things are things we can't fix with machine learning. So that's what I mean by group fairness. But sometimes when you try to make, let's say, an algorithm more fair for one protected group, then you do some adjustments to your model, then it could make it more unfair for another protected group. So then there's even sort of competing things in between these different protected groups. So it can get very difficult to try to fix models, and it's not very easy to fix the models, quite honestly. So most of what we should be doing as practitioners is like just sort of understanding if the models are unfair, and then making decisions based on that. It might involve actually trying to fix the model directly or fix the data directly, but sometimes these things are just not fixable, and that's just something that we have to sit with. So, and like I said before, the law and the policy, even within a single country like the U.S., the laws are, it's a moving target. Things are changing over time. Like it's very, there's a whole sort of subset of people that are just focused on compliance issues. So if you're in any kind of regulated industry, you probably know about this stuff, like lending, for example. Okay, so what's an example of some of the things that we should know about as, let's say, data scientists or practitioners when we're comparing, we're trying to evaluate these things for our model. So one of the most commonly used methods in machine learning fairness is called disparate impact analysis. There's a handful of different metrics which can be used to measure the disparate impact of a model on different subgroups. So, at least in the US, legal theory uses the, quote, disparate impact principle, which means a practice is considered illegal discrimination if it has a disproportionately adverse effect on members of a protected group. So, and disproportionately adverse is usually defined using what's called the 80% rule. So this nice image from WikiHow, which is actually a great site for pretty much anything you can Google. I found it just had like a very nice image trying to make this simple. So basically, this is how you calculate it to find out if you're within the 80% safe zone or not. This is just giving an example of, let's say you have men and women applying for a position. If women are selected for the same position at a rate lower than 70, like let's say the rate of selection for men is 90% for this position. I don't know how you would select multiple people for a position, but let's just go with it. And if women are accepted at 72% or higher, then that would be basically 80% of what the men are, so that's considered okay. But if it's lower than that, then we're starting to see like, there's actually quite a bit of a difference between these two groups. So that's just, it's very, very simple math that you're doing here. And we have something that we call the adverse impact ratio. And so generally, the way that you do this is you calculate the AIR, or adverse impact ratio, for different group comparisons. And let's say, so it's on a pairwise level. So let's say you compare white men to black women. And if the AIR is, let's say, 0.6 or 0.7, that would be evidence that there's a disproportionate impact between those two groups. That would mean that it's not a good situation. It's discriminating against probably the minority group, and this is not a good model to use. There's other metrics that you can use to calculate. There's something called marginal effect. That's for classification. For regression, we have different metrics. There's something called standardized mean difference. These are just a couple examples. There's other things. But in terms of like what's accepted in terms of like legal stuff in the US, adverse impact ratio is a very popular metric that's used. Okay, so what do we do if we find out that our model is actually discriminatory? Here's what you would do. So one thing is you could train a bunch of models and do a disparate impact analysis on all the different models and see if there is one in your set that doesn't suffer from that. If there's really a problem within the data, it's probably unlikely that some of your models are suffering from disparate impact and some of them are not. However, that can be the case. So that's why it's good to, evaluate this on a whole bunch of models. And if you're able to just find one without doing any work that satisfies these criteria, then you can just choose that model and throw the rest away. But if there are no, fair models, then what can you do? So there's a couple different approaches that you can take. One, you can try to fix the data. So that might be something like maybe there were just not enough data points from the minority groups in your data set, and maybe if you just added more, the model would be able to learn better and to discriminate better between different things, and you would end up having a model that was fair. So that's one thing. That doesn't always work, and it's potentially questionable for lending and insurance and hiring. Like I said, all of this is very much on a case-by-case basis, so it has to be evaluated by, if you work at one of these types of companies, by your compliance team or something like that. Another option would be like to try to fix the model, or some of the time you would take all these approaches at the same time. So to fix the model, that might be something like you could leave the demographic features in the model and try to regularize the impact manually. So you could, there's ways, it depends on what software you're using and how easy they make that for you to do. But one of the examples that I had before of the partial dependence plots were like, if you left in, let's say, the demographic variables, you could put some kind of constraint on that would, force something that would help to fix this. But that's also, not that effective, I guess. So the other, another approach is you could still remove the demographic features from the model because, you really don't want the model to learn from them. And you could use some kind of dual optimization functions that measures fairness and accuracy at the same time and then optimizes for that. So I haven't actually seen that in any kind of widely used software, but if you were writing some custom stuff yourself, you could probably do that. But that would really require rewriting the machine learning algorithm itself to optimize two things instead of one, which is typical. So that's a little bit harder. There's something called adversarial debiasing, which is kind of a new approach from Google research. Might be okay for regulated work if the demographic features are not in the model, but that's also very new, researchy, so it would probably be hard to get away with that from a compliance perspective. Another thing is you can just fix the predictions themselves, so you can sort of reweight after the fact some of the predictions on the minority groups to try to achieve fairness. That also might work okay, but also could be questionable in terms of compliance. So, I'm not giving you a lot of exciting things here, but, there are ways to do this. But I think we're, as an industry, at the point where we're really starting to get serious about building these tools. So I would guess that like a year or two from now, a lot of this stuff will be much easier. So, stay tuned. And there's a lot of active research in this field right now, so there could be new methods that we don't have today that could solve a lot of these problems. So it's a really hot, exciting field with a lot of really rewarding results at the end if we do solve this. That's the goal. So let me talk about some of the stuff that we're trying to add in H2O Auto ML related to this. So this is all work in progress. We're going to probably have some of this stuff coming out for the first time in our next release in September of H2O, so 3.32. We're going to have some interpretability stuff. We're not ready to release the fairness stuff yet, but we've got a whole bunch of things in the works. So work in progress, we've got feature importance comparisons. We've got Shapley, so there's something called tree shap, which is a way to, I guess I didn't define all of these methods, but these are just common interpretability methods and stuff that we already have built into H2O that we can use with AutoML. So I'm not going to go into too much detail, but Shapley is just a method to kind of understand the individual, like for a particular row or a particular person in your data set, you can understand in a lot of detail which features are impacting that particular person's prediction. And it can change from row to row. So it's different from global feature importance, where it's saying generally these are the most important features for the model. This is more like, for this particular person, these are the exact features and their contributions that led to the prediction, so that can be very informative. Partial dependence plots. There's another thing similar to partial dependence plots called ice plots. They're also useful. We're giving you the ability to constrain the model. So that's the example that I gave, where you're trying to force a relationship between income and whether or not somebody got the high interest loan. Then related to fairness, we're working on disparate impact analysis and then other fairness metrics. So this is all work in progress, but this is stuff that we're trying to add to H2O Auto ML. Here's the demo. This is something maybe, to visit later, but this is just kind of an idea of, it's really just a prototype of what we're building inside of H2O. I just built it in R. So what you would do is you could use this function. Right now we're just calling it get disparate impact analysis, and you give it, AML is just the name of like an AutoML object. You could also just pass a single model, but basically it would just calculate for all the different subgroups. So remember that when we talk about these metrics, it's the pairwise combinations that we're looking at. So we're looking at two different groups, and then we're calculating a metric. So if you have many, many different groups, and you can do combinations of things, like you can do race and gender at the same time. So like I said, comparing white men to black women, or Asian men to white women, or et cetera. So we want to calculate all those group comparisons, and then see if there's any discrimination among any of them. So we don't want to just look at what we think is going to be obvious, or just, one or two things. We really want to calculate all the different combinations and see if there's anything in there. So that just does that automatically for you. And it allows you to specify which columns you're interested in looking at. So in this case, we're going to look at all different groups of, in this case, it's not gender, but sex and race. And then for a particular model, you can, here, I'm actually just going to show you what this looks like on the next slide. But first I'm going to show you what we would have on the leaderboard. So for the first function, this is kind of what you would get. You get the regular AutoML leaderboard, but then we're going to get some AIR metrics in there. So I'm actually deleting some columns from this image here because I can't fit them all. So I'm just showing you AUC, which is the performance metric, and then I'm showing you we have AIR min, mean, and median, because remember, we're calculating AIR for all the different pairwise comparisons. So we're just looking, is there any adverse impact in any of those combinations? And so we want AIR min to be greater than 0.8, because if it's not, that means that we do have evidence of adverse impact in some subgroup. So in this case, we ran this for all the models, and unfortunately, all of the models had discrimination in them. Some more than others, but we have this flag on the end, adverse impact equals true. So this is, this is an alert. This is like a red flag, like something's wrong and you need to look into it further. So then we move on to the next function where we say, okay, what is actually going on here? Who is being discriminated against? What's going on here? So you can then, with the second function, calculate and see all the things that were calculated here. So it has all the different groups here enumerated. So it will also just look at female alone versus male alone, and then it will also do like the combinations of like female Asian, male Asian, etc. So if you want to like see what we're looking for, look at the AIR column and look for anything that's less than 0.8. So what do we have? I mean, one obvious thing that I see is on rows 12 to 14, we have that AIR is less than 0.8, and it's actually all the way down to 0.62 for Black females. are being the most discriminated against in this mortgage lending data set. Oh, I didn't actually explain what this data set is in detail, but if I go back, this is the Home Mortgage Disclosure Act data. So it's by law, lenders are required to report the information about the people that applied for loans, and then what was the outcome? Did they get a loan? Did they not get a loan? Did they get a low interest loan or a high interest loan? So it's very important that we have laws that kind of force this kind of disclosure, because this is how we know about this stuff, because otherwise we really have no idea if any of this is happening. We just have to, assume that it's happening quite widely. But so this is just one simple example of like what could we do, and then from here we're not going to go into detail about how to remediate this or how to try to fix this model, because we're just kind of not there yet. But the first thing that we need to do is just give people the tools while they're building the models to identify these problems, and to make it very easy, and to make it just part of the automatic process that's happening. Because if we make it, sort of not automatic, or some obscure function in the software, probably people are just not going to use it, either because they don't know about it, or for a lot of other reasons. So the goal, I think, now, like with software that we're developing at H2O, is like, what can we do to help people have this information? And whether or not they use it, that's outside of our control, but we want to do everything in our power to make it as simple as possible, so that there's not a lot of excuses about, well, I didn't know about this, or I don't know how this works. And we want that not to be an excuse anymore. So it'd be great if people could be aware of this issue and start thinking about, start to actually feel empowered that they can understand this stuff, and that they can do something about it, and they can be aware of it as a data scientist. Because you might think, as a data scientist, how is this my job to worry about? That's somebody else's job. But let's make it our job. I think this is like, there's a lot of issues in society related to discrimination, and if there's any way that you can help, it's great to help. So I just have a couple slides left. I want to save enough time for questions. I should probably stop talking in a minute or so, but I just want to say a few more things, and then I'll probably skip the rest of my slides and you can look at them later. But another thing I just want to emphasize is, like, when is it really not appropriate to do machine learning at all? I want to quickly bring this up, because sometimes people get focused on, like, oh, I'm a technical person, I'm going to solve this problem with tools and technology, and you get focused on, like, I need to just minimize differences in accuracy between subgroups, and you get too focused on that. And then sometimes there's really just, maybe you should be thinking more broadly, like maybe some of the models that are out there should just not be built for certain use cases. So you might want to just consider this as you're doing your work. Could your model harm people, and especially marginalized groups? Is this doing anything where we're shifting power, in some way? I'm not going to go into details about that, but and then some more technical things, like, does it fail on outliers? That's something to watch out for. Maybe if you can't build a model that's not capable of doing that, you shouldn't put that into production. Another thing is, like, does your model have strong confidence about wrong answers? And I'll show you quickly something about that. But yeah, this is just, if you're new to this field, I just want to introduce you to some of the people that you should know about and follow. Timnit Gebru, she's one of the co-leads of the ethical AI practice at Google. I would just highly recommend Googling her and looking at her work. She's been a pioneer in this field. And another group is called AJL.org, so algorithmicjusticeleague.org. It's a nonprofit that's trying to bring awareness and really do a lot of research related to this. We really don't want to be in a society, at least I don't, I can't speak for everybody, where, somebody's just knocking on your door, dragging you off to jail and saying the computer says, you got to go to jail, get in the car. Like, that's just a terrifying reality. So there's lots of cases where algorithms are in fact doing this right now. and it's very concerning. And then there's just cases of just bad machine learning. So somebody is trying to basically build an image classifier that can detect whether or not you have COVID by doing, an X-ray of your lungs. And so these models, they're not trained on a whole lot of data, but the models themselves had like very high confidence that they were right about their predictions, but then somebody took a picture of a cat and gave it to the same model, and it was like 100% sure that it was COVID. And, so like, what are we doing here? So we have, these are things where you think you have a great model. You really need to be very careful about this stuff because some of what, the models that people put out there, they just really don't work. So I'm going to skip through the next section. It's really just a bit more detail, and then I want to leave time for Q&A. Here's some resources. So if you're new to H2O, you want to try it out. Again, that link down there is for the USAR talk that has the demo with the algorithmic fairness and the home mortgage lending data. There's my contact, and so then also I will just leave this last slide up for Q&A. And then if you want to, driverless AI is our other tool that you can try out. There's a link there if you want to try it out as well. And there's a number of different interpretability methods also in driverless. So Shabar, do you want to kick off some Q&A?
Yes, thank you, Erin. Thank you for that. And we do have a lot of questions in our chat window, so we probably won't be able to get through all of them, but stay tuned on our website. We will probably write a blog about it. Let's go to a question here. Do you have a framework to check the fairness of the model?
So that is what we're building right now. So you can try it out. So we have a prototype that's on that link. Let me go back here, that USAR 2020 link. So that's just where I put the materials. It's sort of it's in R only. So if you were looking for a Python one, we don't have that yet. But yeah, that's what we're doing. We're trying to do exactly that by checking the fairness.
Great. Do you have any advice for how to convince leadership or stakeholders that interpretability and fairness is important?
Yeah, I think that, one thing that's great is that it's being taken seriously by big companies now. So, a lot of the big, what we consider big tech companies like Google and Microsoft, et cetera, like have ethical AI teams that are taking this very seriously. And like, it's actually come a long way in the past 5 years. It used to be quite a niche topic that was sort of more of an activist social justice, thing at the time, or at least it was viewed that way, and something outside of the scope of what a data scientist does. But I think that mindset is changing quite a lot. So I think just pointing them to the work of, maybe some of the videos on YouTube of these people like Timnit Gebru and Margaret Mitchell. There's so many people that are doing a lot of interesting talks on this stuff. And so I would just say, like, one thing would be just sharing resources about this stuff with your colleagues or your boss or whoever, and then, give them a real live example. And you could point to the demo that I have listed here. You could make your own example using the tools that I gave you. You can wait until we have tools inside of H2O released to do that as well. But I think, if you're able to just take the demo even that I have just now with the prototype and use it on your own data and show that there's, some unfairness among different groups, that's pretty convincing argument. So I think most people want to do the right thing. They're just unaware of this topic, and they're unaware of how to measure it. They know there's ways to measure it, but they don't know how. They don't have the scripts. They don't have the code. So what we're trying to do is give you that code so that you can do this, and to make it as easy as possible. Then from there, then it's your job to try to convince people, but at least you're coming prepared with the data and the evidence, and really just, just pointing people to stories on the internet of how things have, how people have been harmed by algorithms can be convincing as well.
Great, thank you. Would excluding sensitive features like ethnicity, gender, etc. from the model training data set still result in unfair models?
That's a good question. So that's kind of the traditional approach is just, oh, what if we just, if we remove these features, then obviously the model can't learn from them, so it can't be discrimination. But in fact, that's not usually the case. So pretty much all the time, there's at least some, if you're dealing with an actual legal compliance issue, there are specific attributes that you cannot include, like race, sex, etc. And but they don't specifically prohibit other variables that might be correlated with that. Like the sort of canonical example is zip code. So if you have zip code in there, that's generally a proxy for some kind of some kind of racial indicator. So different zip codes have different demographics of people. So if you have that in there, you are in a way feeding the model with information that you didn't mean to give it. So when I did the home mortgage data demo, I actually trained the model without those features in it. And even so, it was able to somehow learn, to treat those two groups differently, or all these different groups differently. So that's why you have to, even if you don't have the data in there, I mean, you actually need the data to be able to check whether or not it is discriminating. So that's kind of a, sometimes people think maybe we shouldn't collect that data so that we don't have it and we can't use it, but you actually kind of need that data just to even do the check. So I would say if you are making a choice of collecting that data or not, definitely keep the data because you need it to be able to check the different groups. But yeah, the data, the models learn to discriminate anyway, not all the time, but I mean, certainly removing the variables is better than not removing it, but what we've seen is that that's not always the case.
Great. How can you protect against fair washing?
That's a good question. So there's this concept of, well, maybe a term called, fair washing, or it's sort of like whitewashing, or, that type of thing where what people are really looking for is to sort of offload the accountability onto a tool or an algorithm. They're like, oh, the model says it's fair, so we're good, and then they move on. So what I am nervous about is that as we see more of these tools for algorithmic fairness, that I hope that the authors of the tools really take care into trying to not reduce this to, and even the terms that they use in the software themselves. So, one of the things that we considered was, do we add a little column that says fair or not fair? And we decided not to do that because we don't want to be used sort of to say, oh, H2O model said it was fair, so we're good. And we want to just be careful about using the word fair, because it is kind of like once you get the little fair stamp, then you can move on and you can absolve yourself from any responsibility. So, so it's just important to know that even if you don't have evidence of adverse impact, let's say, there could be other things in your pipeline or how the model is applied that are unfair objectively. So that's my main concern is, as we see more and more of these tools, is this just going to be used to kind of like check a box, like, oh, we checked for fairness, it's fair. So that should be a takeaway from this talk, is that is not sufficient, and hopefully, you think about the problem on a more holistic level.
Thank you, Erin. Looks like that's all the time we have for questions. We do have a lot more left, so everyone stay tuned on our social channels, and you can see any updates on those questions there. I want to thank you, Erin, for taking the time today and doing a great presentation. And I'd like to say thank you to everyone who joined us today. The presentation slide and the recording will be made available after this presentation is over. So have a great rest of your day, everybody. Thank you.